Welcome to our exploration of hydrocarbons. In this presentation, we will dive deep into the three fundamental classes of hydrocarbons: alkanes, alkenes, and alkynes. These organic compounds, made entirely of carbon and hydrogen, form the backbone of organic chemistry and modern civilization. From the methane that heats our homes to the ethylene that makes our plastics, understanding hydrocarbons is essential for any chemistry student. Let us begin with the simplest family, the alkanes. Alkanes are saturated hydrocarbons, meaning every carbon atom forms four single covalent bonds. Their general formula is CnH2n plus 2. The simplest alkanes are methane with one carbon, ethane with two, propane with three, and butane with four carbon atoms. All carbon atoms in alkanes are sp3 hybridized, giving them a tetrahedral geometry with bond angles of approximately 109.5 degrees. These molecules are nonpolar, making them soluble in organic solvents, but insoluble in water. As the carbon chain lengthens, boiling points increase due to stronger London dispersion forces. Methane through butane are gases at room temperature, pentane through heptadecane are liquids, and longer chains are waxy solids. Naming alkanes follows systematic IUPAC rules. First, identify the longest continuous carbon chain to determine the parent name. Then, number the chain to give the lowest possible numbers to any substituent groups. Alkyl groups like methyl, ethyl, and propyl are named as prefixes with their position indicated by a locant number. Butane with four carbons has two structural isomers, normal butane and isobutane, also known as 2-methylpropane. Pentane with five carbons has three isomers. The number of possible isomers grows rapidly with carbon count. Decane has 75 possible isomers. Alkanes are generally unreactive due to their strong nonpolar carbon single bonds. However, they undergo three important types of reactions. First, combustion. The complete oxidation of alkanes produces carbon dioxide and water while releasing large amounts of energy. Incomplete combustion produces carbon monoxide and soot. Second, free radical halogenation replaces hydrogen atoms with halogens like chlorine or bromine. This reaction requires ultraviolet light or heat to initiate the radical chain mechanism. Third, thermal cracking breaks large alkane molecules into smaller, more valuable ones using high temperatures and catalysts. These reactions are the foundation of the petroleum industry. Now we move to alkenes, which contain at least one carbon-carbon double bond. Their general formula is CnH2n. The double bond consists of one sigma bond and one pi bond. The pi bond makes alkenes much more reactive than alkanes. Ethene, also called ethylene, is the simplest alkene. Its carbon atoms are sp2 hybridized, giving it a planar geometry with bond angles of 120 degrees. The carbon-carbon double bond is shorter than a single bond, 1.34 angstroms compared to 1.54 angstroms. The pi bond is weaker than the sigma bond, which is why it breaks easily in addition reactions. Alkenes can also exhibit cis-trans isomerism due to restricted rotation around the double bond. The characteristic reaction of alkenes is electrophilic addition across the double bond. The pi bond acts as a nucleophile and attacks electrophilic reagents. In hydrogenation, hydrogen gas adds across the double bond with a platinum or palladium catalyst to produce an alkane. In halogenation, bromine adds across the double bond, which is why bromine water decolorizes in the presence of an alkene. In hydrohalogenation, hydrogen halide adds across the double bond following Markovnikov's rule. The hydrogen attaches to the carbon with more hydrogens already. In hydration, water adds across the double bond with an acid catalyst to produce an alcohol. Alkynes contain at least one carbon-carbon triple bond. Their general formula is CnH2n-2. The triple bond consists of one sigma bond and two pi bonds. Ethine, commonly known as acetylene, is the simplest alkyne. The carbon atoms are sp hybridized, making the molecule linear with a bond angle of 180 degrees. The triple bond is even shorter at 1.20 angstroms and stronger than both double and single bonds. However, despite being stronger, the triple bond is reactive because the two pi bonds are exposed. Terminal alkynes have a unique property. The hydrogen attached to the sp hybridized carbon is weakly acidic, with a pKa of about 25, which is far more acidic than alkanes or alkenes. Alkynes undergo similar addition reactions to alkenes, but they can add two equivalents of reagent across the triple bond. Complete hydrogenation converts the triple bond all the way to a single bond using excess hydrogen and a catalyst. Partial hydrogenation using Lindlar's catalyst gives a cis-alkene, while reduction with sodium in liquid ammonia gives a transalkene. The unique reaction of terminal alkynes is deprotonation by strong bases like sodium amide to form acetylide ions. These acetylide ions are powerful nucleophiles that can undergo substitution reactions with alkyl halides, allowing us to build larger carbon chains. Let us compare the three hydrocarbon families. As bond order increases from single to double to triple, bond length decreases and bond energy increases. Alkanes with sp3 hybridization are tetrahedral, alkenes with sp2 are planar, and alkynes with sp are linear. Alkanes are the least reactive, undergoing only substitution and combustion. Alkenes add electrophiles across their double bond. Alkynes are the most reactive toward addition and also show unique acidity. This progression from saturated to unsaturated hydrocarbons is one of the most elegant patterns in organic chemistry. Hydrocarbons are the foundation of modern life. Natural gas, primarily methane, heats homes and generates electricity. Gasoline and diesel, mixtures of alkanes, power our vehicles. But hydrocarbons are not just fuels. Ethylene from alkenes is polymerized into polyethylene, the world's most common plastic used in packaging, bottles, and containers. Propylene is used to make polypropylene. Acetylene is used in welding torches that reach 3,500 degrees Celsius. Benzene and other aromatic hydrocarbons are starting materials for pharmaceuticals, synthetic fibers, and dyes. Over 90% of all organic chemicals are derived from petroleum hydrocarbons. Time for a quiz. Question 1. What is the general formula for acyclic alkanes? Option A, CnH2n. Option B, CnH2n plus 2. Option C, CnH2n minus 2. Option D, CnH2n minus 2. Option D, CnH2n plus 1. Take a moment to think. The correct answer will be revealed shortly. Quiz question 2. What type of reaction is characteristic of alkenes? Option A, substitution. Option B, elimination. Option C, electrophilic addition. Option D, free radical polymerization. Think carefully about alkene chemistry. The answer will appear after the timer. Quiz question 3. Why are terminal alkynes acidic while alkenes and alkanes are not? Option A. The triple bond is longer than a double bond. Option B, the CH bond in sp hybridized carbon has Morse character. Option C, alkynes have more hydrogen atoms. Option D, the triple bond repels the hydrogen atom. Consider hybridization and orbital character. Quiz question 4. How many structural isomers does pentane C5H12 have? Option A, 2. Option B, 3. Option C, 5. Option D, 8. Think about how many ways you can arrange 5 carbon atoms. Quiz question 5. What is the main industrial use of ethene C2H4? Option A, as a fuel for vehicles. Option B, as a monomer for polyethylene production. Option C, as a solvent in dry cleaning. Option D, as an anesthetic in medicine. Think about the scale of plastic production worldwide. Worked problem 1. Classifying hydrocarbons from their formulas. We are given 5 molecular formulas and need to classify each as an alkane, alkene, or alkyne. For C5H10, the formula matches CnH2n, so it is an alkene with 1 degree of unsaturation. For C6H14, it matches CnH2n plus 2, making it a saturated alkane. For C4H6, the formula matches CnH2n minus 2, so it is an alkyne with 2 degrees of unsaturation. For C7H14, again we see CnH2n, so it is an alkene. Finally, C2H2 is ethyne, also known as acetylene, matching CnH2n minus 2. Worked problem 2. IUPAC naming of hexane isomers. We need to draw and name the three C6H14 isomers. First, the straight chain isomer is N-hexane. Second, we add a methyl branch on carbon 2 of a pentane chain, giving 2-methylpentane, also called isohexane. Third, we add two methyl groups on carbon 2 of a butane chain, giving 2,2-dimethylbutane, also known as neohexane. Remember, hexane has a total of 5 structural isomers, but these three demonstrate the key branching patterns. Worked problem 3. Calculating degrees of unsaturation for C8H12. First, a saturated alkane with 8 carbons would have the formula C8H18. Our compound has 12 hydrogens, which is 6 fewer than the saturated reference. Each degree of unsaturation removes 2 hydrogens, so 6 divided by 2 gives us 3 degrees of unsaturation. This could mean 1 ring plus 1 double bond plus 1 triple bond, or 3 double bonds, or 1 ring plus 2 double bonds. Worked problem 4. Combustion analysis of an unknown hydrocarbon. We burn 1 gram of the compound and obtain 3.14 grams of CO2 and 1.29 grams of water. First, find moles of carbon. 3.14 grams divided by 44.01 grams per mole gives 0.0713 moles of CO2, so 0.0713 moles of carbon. Next, find moles of hydrogen. 1.29 grams of water divided by 18.02 grams per mole gives 0.0716 moles of water. Since each water contains 2 hydrogens, we have 0.1432 moles of hydrogen. The ratio of carbon to hydrogen is 1 to 2.01, approximately 1 to 2. Therefore, the empirical formula is CH2. This could represent an alkene or a cycloalkane. Worked problem 5. Markovnikov addition of HBr to propene. Propene is CH3, CH double bond, CH2. When HBr adds, the hydrogen can attach to either carbon of the double bond. If hydrogen attaches to carbon 1, the terminal carbon, we form a secondary carbocation, which is more stable. If hydrogen attaches to carbon 2, we form a primary carbocation, which is less stable. The reaction proceeds through the more stable secondary carbocation intermediate. The bromide ion then attacks the carbocation, giving 2-bromopropane as the major product. Let us summarize what we have learned. Hydrocarbons are the simplest organic compounds, composed only of carbon and hydrogen. They are classified by the type of carbon-carbon bonds they contain. Alkanes have only single bonds, sp3 hybridization, tetrahedral geometry, and undergo substitution and combustion reactions. They are saturated and relatively unreactive. Alkenes contain at least one double bond, sp2 hybridization, planar geometry, and undergo electrophilic addition reactions. The pi bond is the key to their reactivity. Alkynes contain at least one triple bond, sp hybridization, linear geometry, and undergo addition as well as showing unique acidity. As bond order increases, bond length decreases, and bond strength increases. Hydrocarbons are the foundation of fuels, plastics, and petrochemicals that power our modern world. Mastering these concepts is essential for success in organic chemistry.